So let me go back to this slide and I will just copy this. So what I'm asking is, is H3 a subset? So a vector R2 is also a set of vectors, right? R2 is a set of vectors. And S3 also is defined as a set of vectors. So can you tell me if S3 is a subset of R2? I think everybody is saying that it is. Yes, R2 contains S3, so it will be a subspace. S3 is equals to R2, so it's trivially yes. So we saw that, okay, I'll come to that later, that we saw that all the linear combinations of these two vectors actually span the whole R2. We had seen this yesterday, right? In the last lecture, that the linear combination of these two vectors were actually spanning the whole R2. So whatever vector I take will be in R2 itself. So trivially, this is actually the subset of R2. Fine, this is clear, right? So I have to, yes, so this is correct, that S3 is a subset. I will say subset, and then I will also say that S3 is actually a subspace. Space of R2. Okay. So the analogy is very similar to what we have to set and subset. So a subspace is actually a space, is actually a subset, like it will contain the subset of the vectors from a vector space V, and it will follow all the properties of the vector space, which are like additive properties, some multiplicative properties, and the closure properties. And it's also closed under the vector addition. So whatever vectors I have taken from the subspace or subset will all, and if I add them, it will belong to the subspace or the subset. If I take the scalar multiplication of any vector that I take from the set or subspace, it will also belong to the space or the subset. Right. Fine. So a subspace of a vector. So just reiterating this again, that a subspace is actually a subset of the vector space and it follows all the properties. So it follows additive properties, multiplicative properties, and closure properties. Also, we have to ensure that whatever vector we are taking from the subspace, the sum of those vectors should belong to the subspace. And whatever vector we are taking from the subspace, the multiplicative of this vector should also belong to the subspace, which is similar to what we have seen in the additive and multiplicative and closure properties of the vector space. Fine. Cool. So now let's find subspaces of R2. So can anyone tell me a subspace of R2? So there'll be a trivial subspace. I'll just eliminate that. It's equals to R2. Okay. Rohan is saying R. Okay, I wanted somebody to say this so that I can clarify this. Okay. Yeah. Okay. Let me take a slide here. Is R a subspace of R2? Okay, so Rohan is saying 0 vector, R2 are the trivial ones, and any line passing through the origin. But somebody also said that R is a subspace of R2. Is this true? Okay. So what do we have in R? What are the vectors looking like? So we have vectors like this, right? and R2 vectors look like this. X-axis. Okay. Rohan is saying that he meant x-axis, which is basically a line. Fine. But I wanted somebody to say this because this is one of the most misunderstood thing. One of the most misunderstood concepts. So see, R is not even a subset of R2. Okay. Because the coordinates needed to represent R2 and R1 are very different. Right. So for representing R2, I need two coordinates. And to represent any vector in R, I just need one coordinate. So it's not even a subset. And if it's not a subset, I will not get the subspace as well. Fine? Clear? Dimensions are different basically. Yeah. But I don't want to use the word dimension. It just see that this vector. So I told you already that a subspace is a subset of a vector space, right? So leave away the additive properties, the multiplicative properties, and the closure properties. Just tell me, does this vector belong to R2? So I'm asking the question. Does this vector 1 belong to R2? No, right? But if I had asked, so this is no. But if I had asked this, you would have said yes, because it has two coordinates that I can use to represent it. So this vector, this particular vector, if I just look at this vector, this is not even in the subset, any subset of R2. So that's why R is not a subspace of R2. Fine. So, okay. So I have already received a lot of answers. So x-axis or any line passing through origin. Origin. And also I had a very interesting answer. The zero vector, right? Zero vector. So zero vector, it's, let me not call it zero vector, this. Right? So this, it's itself a subspace. Can you guys see how? That this is a subspace. So if I multiply anything with zero vector, it will always give me the zero vector, right? And A belongs to R, right? If I add zero vector to the zero vector, I'll get zero vector. I minus zero vector from the zero vector, I get zero vector. I do any operation to the zero vector, it's still in this set, right? So this set is actually a special set. It's called zero space, zero subspace. This is called zero subspace. Subspace. Okay. So this is a trivial, again, a trivial subspace. Fine. Fine. It's closed under addition, multiplication, and itself at origin. True. And also any line passing through the origin, which means that any vector I take from X, any vector, I will take it to the next slide. I'm coming to that line passing through the origin only. So, okay. So I have any vector. So I have R2. Okay. Let me take any vector X belongs to R2. Fine. If I do C of X. C of X. C of X. Right. And I take this as a set. Right. Is this a subspace? So some people are saying that it is a subspace. Now let's visualize how will this look like. So we had seen this yesterday, but I will again show you that what is this is. So first of all, see that it will pass through origin, because when I take C to be 0, this vector will become 0, right? So Cx is equals to 0 of whatever vector I have. So this will be just a 0 vector. This is clear? So this particular set will contain 0 vector, right? And when this will contain 0 vector, whatever set this is, all the points that lie in the set, whatever space they are making, that will pass through the origin. That's what we say, that this is the line passing through the origin. Okay, let me show you on the GeoGebra. I think that will be more clear. So suppose I take a vector. I'll take a vector 1, 1. Fine. This. Fine. Now let me take the multiples of 1, 1. I will do A times U. And I will do settings. Let me show you the trace of this. And I will also play with this. Right? And I'll take this to this. Right? So these are all the multiples of 1, 1 vector. Fine. Let me change the vector to say 1, 2. Right? So 1, 2 vector I changed. And now if I do the same thing, you will see there is a line that we are getting. We had seen this earlier, that all the multiples of a vector are actually a line, right? I can change it to any vector. I can actually change it to, I moved the vector by mistake. Right? I can take any vector. I will take A1, 7. There is another line. I will take 8, 1, 8. Another line I'll get. Right? I am getting another line again. Then I can change any vector basically. 3, 4. Right? This is a vector. And if I see the trace of this, this is a line. So only the multiples of a single vector will actually form a line. And that's what we meant, a line passing through the origin. This is clear? So Cx is actually a line passing through origin. Clear to everyone? Fine. Okay. Moving on. So I already told you this we already covered. Now let's do the vector space sum of the subspaces for R3. Can you guys tell me any subspaces for R3? Don't tell me R2. So first of all, trivial. We'll write the trivial subspaces. Trivial subspaces. So Z, which is the 0 vector. Right? Then R3 is also a subspace of this. Then we have, say, any vector that belongs to R3. I can say C of X, and where C belongs to R. Plane containing, yeah. So these are trivial ones, right? Now we have also, there can be one more vector. Sorry, one more subspace. So that is actually the plane passing through the origin, like Rohan said. Plane passing through origin. Through origin. So I'll just write, this is the first one, second, this is the third one, and this is the fourth one. Fine. So a plane passing through the origin. Hannah, how will we get a plane passing through the origin? Anyone? So yeah, so if you take same vector, will it be a plane or a line, Sameer? Yeah. So if I take these two vectors, 1, 2, 5, right? And I take all the linear combinations of any two linearly independent vectors, like Rohan already said, and I define my subspace is this, and I will take A plus B times of this. Then this is my subspace of R3. Fine. So it'll be a plane. Fine. Let's see if it will be a plane. 1, 2, 3, and 1, 2, 5. Let me come to the 3D calculator. I'll just change it here. 1, 2, 3, and 1, 2, 5, right? 1, 2, 5. You guys already said 1, 2. Right, so you can see my U vector is, I will remove this P vector, we don't need this. So U is 1, 2, 3, and the V vector is 1, 2, 5. And I will take all the linear combinations of this. Right, I'll just play this. And I'll show you this trace of this. Trace. It's not showing up. Yeah, it's showing up. It's just beautifully forming the whole space. Right, so it's a plane. Everybody can see, right? So this is a plane, and it's also passing through the origin. Fine. So any two vectors. Fine. You guys are going ahead of the class. That's good. Fine. So a plane that is passing through the origin is also a subspace of R3. Great. Okay. So I already had this question for you. That is R2 a subspace of R3? Now, can everybody answer? Is this the case? Okay. So because R2 is not even a subset of R3, R2 is not a subspace of R3. Awesome. Now, we have seen what are subspaces. Now, I will give you some sets and tell me what should I add to them so that it becomes a subspace of whatever corresponding vector space is. So, if this will be the subspace of R2, right? So, tell me what should I add to S4 so that it becomes a subspace. Question is clear, right? Yeah. So I will add multiples of 1 and 2. Sorry, multiples of vector 1, 2. Where C belongs to R, right? And what will it look like? It will be a line, right? We already saw this. A line passing through origin. Line passing through origin. Great. Now tell me what should I add to S5 so that it becomes a vector subspace. So what I'll add, like you guys are right, I'll add A of 1, 2 plus B of 2, 3, this set, where A and B belongs to R. So if I take every combination of this, will it not cover all the vectors from R2? We'll come to that in a while, actually. And what will it look like? So I have two vectors and I'm taking linear combination of two vectors. What does it give me? Fine. So I have two vectors. So it will be a plane passing through origin. You guys are also right. This will also be R2 origin. Fine. Okay. What should I add to this so that it becomes a subspace? Okay. Some people are saying it's already one. It's already a subspace. Others, let me know what should I add to S6 so that it becomes a subspace. Okay. Now both is also saying that it's a subspace. Others, please reply. So this is already a subspace, right? Because we talked about it. So this is actually a special subspace called Z. And if I add 0 to 0, I will get 0. If I take a multiple of 0, correct. So this is also 0, right? So this is already a subspace. Already a subspace. Okay. And what it looks like. This is a 0 vector or a, yeah, this is just a 0 vector. Fine. Clear to everyone? This is actually important. This is something that GATE can ask because it's not very trivial to understand, right? So this is important to understand that 0 vector itself is a subspace. Fine. Okay. Now now what should I add to S7 so that it becomes a subspace of R2? Okay. Okay. I will ask some other question. What should I minimally add? Minimally add. Okay. Can you give me an equation rather than saying that all the other vectors from R2 except these? Try to come up with a minimalist equation of vectors that if I add that particular set to this becomes a complete subspace. Okay, you guys are giving me good answers. So all I need to do is I need to do this 0 and 1, right? If I do this, add this set where A and B belongs to R, and I add this, it will cover all the vectors which are there in R2, right? We had seen this. This is a special set. We had seen this yesterday, but I didn't specifically talk about it. I'll talk about it in a while. But tell me, if I do this, do I need to add something else to this set? You're also right, Samir, that we can add linear combination of any two linearly independent vectors. I'll come to that in some time. But if I have to take the linear combination from these vectors, can everyone tell me if they understood that if I take just the linear combination of these two vectors, it will be good enough for me to make the subspace? Why is that, by the way? Because 1, 1 is nothing but 1, 0 plus 0, 1, right? So if this is there, this is already there. But if I take all the linear combination of this, will this suffice? Minimal in the sense is that if you tell me add this A10 plus B of 10. Okay, let me do it on another way. So I have these vectors 10 plus 01. I have these three vectors, right? So if I say that I will add this, here 1, right? Is this already not already not covering, or I should say, C of 1, is it not already the subset of 01 plus B of 10? Is it not the subset already? Right? That's what I meant minimally, that you can just take the linear combination of this and this will already be covered because this vector is actually sum of these two vectors, right? So what is minimal in this? This will be redundant. If I do that, this is redundant, right? Cool. So if I add just these, it'll become a subspace, right? And what will it look like? Plane passing through origin. Okay, let's do one more. What should I add to this set so that it becomes a subspace? What should I add? Okay, so A of 100 plus B of 010 plus C of 001, right? If I add this set, the linear combination, correct? Add this, right? And what will, so this will become subspace of R3. What will it look like? It will look like R3, or we can call it, it will be like a 3D plane. It's called hyper. Yeah, it's a 3D plane. Oh, let me call it R3 only. Let me. This is R3, right? So this is exactly equal to R3. Yeah, it will basically look like a infinite, like going to infinite. It's a 3D space. Whole of the 3D space in which you and me walk on is basically, it look like that. As all are linearly independent, so we need to consider all of them, right? Yes, correct. So all of them are linearly independent. We can see very easily, right? They are linearly independent. So we have to consider them or consider all of them. This will become a little clearer actually in the slides, but that's correct. We have to consider all of them. Because what if I don't consider 001? I will not be able to get the multiples of this using these two, right? Because this is not a linear combination of these two. Make sense? Fine. Okay, another one. What should I add to these, like this set? And I already told you that, okay, tell me, what should I add to this so that it becomes a subspace? Okay, I have one answer. 1, 2, 3 plus B of, okay, you guys are getting it. Awesome. Clear to everyone why I added just this and not a multiple of this? Because this is already a linear combination of these two, right? So if I have to write C, A, B, C is equals to A plus B, right? So I will just add this. What will it look like? Right. So it will be a plane passing through A and B, right? And also origin. A, B are origin. Yeah, we can take first and last one as well. That's not an issue. Actually, can I? 2, 3. Yeah, we can take. Yeah, so there are multiple answers to this. So there is one set, or you can do A of 1, 2, 3 plus C of 4, 6, 8. Right? So we can do any of this. Actually, we can take BC also, linear combination of B and C also. A plus like A is equals to C. So B minus C is equals to A and A minus C is equals to B. But so these two, if I just consider this set, right? Or just the set of, okay, let me come here. Yeah, so I have three vectors, A, B, and C. I forgot the values actually. You can just see that. This is 1, 2, 3, 3, 4, 5. 1, 2, 3, 3, 4, 5, and this was 4, 6, 8, right? So if I take the set A and B, is this linearly independent? Correct. This is. If I take the set B and C, is this linearly independent? This is also right. And if I take A and C, that is also right. So any two of them I take, they're linearly independent. So any two I can take and I take the linear combination of them, select those vectors, put in my set S9, and it will give me a subspace. Right? So I did not understand your question about it. So it will depend on the vectors. To check this, so basically, see, if I take these two vectors, right, this will already belong because this is a linear combination of these two, right? If I take these two vectors, this is a linear combination of these two, this will already belong. And if I take these two also, this is a linear combination of these two, so it will already belong. So if I take linear combination of any two of these and I add them to my set S9, all three will already be there. And it'll also cover the whole space. And it'll become a vector space, a valid vector space, and eventually a subspace. Everybody clear? Yeah, in all the cases, same plane will be obtained. Right. Actually. Yes, correct. Fine. Okay. Let's make this subspace. What will I add to S10 so that it becomes a subspace, a valid subspace? Okay, I have an answer. Linear combination of first two. So I'll call them vector A, B, C. And I will say add. Actually, I should avoid writing this. Let's say U times A plus V times B, where U and B are coming from R. Okay. Others also agree that if we take these two, if I take the linear combination of these two, I will get the subspace. Fine. And what does it look like? So plane passing through. So it's, yeah, a plane passing through A, B, and 0. Fine. Okay. Let's move on. Actually, I have a lot left. Okay. So we already saw that this is a linear combination. It looks like. So this is just the more algebraic function of this, that I will say this is U, this is V, and this is W. And A, B, C belongs to R. Then I just took this, that I have to take the linear combination of these two vectors. Okay. So what is this subspace in terms of U and B? Something that we have seen before. Okay, I missed something in the chat. Yes, for avoiding any confusion. Also see for avoiding any confusion. Yes. Correct. Correct one. So, okay. So coming to this question. So whatever subspace we formed, right? Like the last subspace I formed, and you guys already know it. What is this? This is dash of vector A and B. Or it's a dash of vector U and V. The subspace that I formed. What is this? This is a linear combination, right? Linear combination. This is a linear combination. Also, what is the set of all the linear combination of vectors is called? Something that we had seen. Linear combinations of vectors. How are we saying R4? So I'm saying for I have this du plus dv and u and v is this. So if I take the linear combination of these two vectors and I take the set of all those linear combinations, this is also a subspace. Like I create a subspace here, but this is also called something as span, right? We saw it yesterday, right? So this is called span. We saw it yesterday, correct? Fine. So now I'm going to ask you one question. Tell me, if I have given you two vectors, v1 and v2 in vector space, and h I'm defining as the span of v1 and v2, is h is the subspace of v. Is this true or false? So I have some answers. True, true, false. Okay. Others also, please tell me what's your answer. I have one more true. Okay. Okay. True. True. Okay. Fine. Okay. So let's talk about why we think that it is false. Okay. So I am saying I'm taking span of V1 and V2. Right? When I say span, it means that it has linear combination of V1 plus V2. Right? and A and B belongs to R. No. So I have taken B1 and B2 from a bigger vector space V. Okay. So I had some vector space. For example, I say I have taken this from R3. Okay. So let's assume for some time that V1 or V2 are coming from R3. Now I'm taking the span of V1 and V2. Okay. Now tell me that is this span a subspace of V? Now you get it, Jagat? That this is the subspace of V? No. Will it always be the case that vector not equal always, right? So here, when I'm talking about R3, can two vectors span the whole V? Okay, there's some confusion. Let me go to the basic. Okay. I am taking V1 and V2 from R3. Right? Now I'm taking span of V1 and V2. Take the span of V1 and V2, which is equals to A V1 plus B V2. Right? A and B belongs to R. So I have linear combinations of V1 plus V2, 2V1 plus V2, blah, 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 10V1 plus 10V2, also in the negative directions, V1 plus 10V2, etc., etc., etc. Now, can you tell me, Jagat, whether this will give me all the vectors in R3? Jagat, can you unmute yourself and tell me?
Ma'am,
Yeah.
even no, ma'am.
V1.
It cannot cover all the vectors in R3, ma'am.
Right? So
In
V
my
is not
opinion,
equal
ma'am.
to H, right?
Yes, ma'am.
But H is a subset of V or subspace of V, right?
Okay, ma'am.
Understood, right? Is there any other confusion? Malab, we can clear it right now only. These are
No,
important
ma'am. I am
concepts.
clear, ma'am.
Okay. Right? So, fine. So, this is true. Cool. So, now I have one question. Let H be the vector space defined by the span of vectors, this. Okay? Because I already said that a span of vector actually creates a vector space or a subspace. So, I have defined H to be a vector space or a subspace defined by the span of vectors. And G is also a vector space defined by the span of vectors of these three vectors. Now, the question I'm asking is H equals to G? So I have one answer as yes. Others, please answer. Okay. So I have yes, yes, yes. Others, please complete this. Jagat Varshita, correct? Correct. So someone has already said that this is kind of redundant. Okay. Because this is a linear combination of these two. 2 times this 4, 7 is actually 2 times 2, 3 plus 1, 2, right? Right. So this is kind of redundant. And that's why these two are actually the same vector spaces or subspaces. Fine. So so these two vectors, right? They are actually very special vectors. And they are actually called the basis of subspaces H and G. It's actually vector spaces. Okay. So these two vectors whose linear combination is able to give me the whole subspace are called bases. Okay, so I'm introducing a new term here. These are bases. Okay, let me correct this. 4, 6. Oh, I made a mistake here. Sorry. It's actually 2 times that. That's right. Correct now? 2, 4. Yeah, correct. Thanks for correcting that. So I'm introducing a new term. So these two vectors, the set of minimal vectors, which can give the linear combination of which can give me a subspace, are called basis vectors. That set is called the basis vector. Okay. So I'm introducing a new terminology here, and it's a very simple terminology, something that you have already seen and something that you already understand, that a basis of a vector space V is the collection of vectors with these properties. Okay. So the property is the vector should be linearly independent. So we already saw that these two are linearly independent. And here you guys very correctly pointed out, okay, this is redundant because this is a linear combination of these two, and these are two linearly independent vectors. Okay. So when I say this is the basis, I'm satisfying the first condition that this is linearly independent. These are linearly independent. Right? So I satisfied the first condition. Then they're also spanning the vector space V. Okay. So I said that this is basis for spaces H and G, vector spaces H and G. And you guys already have been telling me that this is span, the linear combinations and nothing just but span. So they are already spanning H and G. H and G, because they are like linear combinations, right? Linear combinations. Correct? So this is indeed a basis. Anybody has an issue with this? That no, this is not a basis. We cannot call this basis. Understood, right? All clear? Clear. Okay. Now let's see basis for vector space R2. Now, based on your understanding so far, can you give me basis for R2? One, 0, 1, 0, 1. Okay. Will there be just one basis for R2? This is standard basis, correct? Infinite basis, right? Can be multiple, right? So the one vectors that we were seeing already, they are also basis, right? Here H and G was actually equal to R2. H and G were already equal to R2. And 1, 2, and 2, 3 were also the basis of R2, right? So this is also there. So any two linearly independent vectors will form basis of R2. Okay? Clear to everyone? Fine. Okay, any set of two linearly independent vectors V1 belonging to can form a basis for R2. So we can have multiple, we can have multiple basis for a vector space. Fine. Now let's do basis for the vector space R3. I will write the trivial one, okay? Don't tell me the trivial one. So this is the standard basis, as somebody already said. This is special because this is very clear to obtain if I want a vector. So X component I can multiply here, Y component I can multiply here, and Z component I can multiply here, and I'll just add them and I'll get it. Now tell me, in general, what will be the basis? So this is standard basis. Standard basis. What are the other bases for R3? We already saw some vectors, right? 1, 2, 3, 4, 6, 7, I'm just assuming that these are linearly independent. 5, 8, 10. Okay, these are linearly independent. Fine. And someone said pi 1, 1. Then you said 1 e. E is, I think, the exponent e, and also 0, 0, 1. Right. Or in general, if I have to say in general, what are the bases for a vector space which is R3? Yeah, Rohan is giving very creative examples. Any three linearly independent vectors belonging to R3, right? Any three linearly independent vectors that belong to R3 will form the basis of this, right? So any set of three linearly independent vectors, v1, v2, v3, which are in R3 can form a basis of v3. So we have, again, multiple bases. Fine. So in general, when I talk about a vector space Rn, any set of n linearly independent vectors, which are coming from that, this is actually Rn can form a basis for Rn. Fine. This is clear? Fine. Cool. Let's find the basis. Okay, this is a very interesting question. Find a basis for a subspace of R4 where all vectors are such that all components are equal. Okay, so there is a subspace. I will call it S lower star, which has vectors like all components are equal. Zero 0.5, 0.5, 0.5, 0.5, or say -2, -2, -2, -2, -2, dot, 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 dot. This is my subspace. Okay, valid. Pi. Rohan and his obsession with pi. Okay, great. Valid, valid. Pi, right? Any other basis? This is also a basis, right? This is also a basis. So I can multiply C 1, 1, 1, 1, and C belongs to R, or any vector from this. Log 1, log 2, log 3, log 4. No, how will this be a basis? Log 1, log 2. Let me write it a little above. This is first basis, this is second basis. Log 1, log 2, log 3, log 4. So log 1 is not equal to log 2, right? Right? So this is not a basis. So I'll remove this. Okay. So I had asked you to find just one basis. So clear to everyone, right? So we can find any basis. So basically any vector which has all the values equal, all 4 coordinate values equal, will form the basis for this vector space. Clear? Just write small note. Okay, I will continue. Any vector x1, x2, x3, x4, where x1 is equals to x2 is equals to x3 is equals to x4 belonging to R, right? So this is the general basis. Sorry. Sorry about this. Looking at the chat. Okay. 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 So now I'm going to define another term, which is called dimension of the vector space. And this is something that somebody was asking. I think Samir was asking in the first lecture itself, and had slightly abused the definition and notations there when I said dimension of a vector, right? So it's not dimension of a vector usually, it's dimension of a vector space, right? And I had just taken the dimension of the vector space to be equal to the dimension of the vector there. But actually, dimension is defined for vector space, okay? And this is how we define it. So the number of vectors in a basis of a vector space is called the dimension of a vector space. Okay. So if I have to talk about this vector space, what is the dimension? 1, because there is just one vector in the, okay, Jagat was saying 4. Why is it 4? So I'm not talking about R4, okay? I'm talking about, let me add this slide here. What is the dimension of a subspace defined as vectors from R4 where all coordinates are equal. Right? So what is the dimension of the subspace? I'm talking specifically about the dimension of the subspace. So the dimension is, okay, correct. So this particular dimension, when I'm talking about this subspace, it only had one basis vector, right? Or the basis had just one vector in it. So for example, this actually formed a basis for this, right? Valid basis, right? And there is just one vector in the basis. Yes, Amit, tell me. There is.
Can I proceed now?
Yeah, sure.
Ma'am, so a subspace of R4 can be a line or it can be a plane as well.
Yes,
How can we say with surety that the dimension will be 1? It can be 1, 2, or 3 also. If
it
it
can
will be
be.
a
It can be. Yeah, it can be. But when I was talking about the dimension of subspace here, I specified what subspace is this, right? So I specifically said this is a subspace where all coordinates are equal. This is coming from this question. Where is that question?
oh, okay.
This is the question that
Oh,
find the basis of the subspace. So this was the subspace. And for this subspace, I was asking the dimension. So this is what I've written. What is the dimension of the subspace defined as vectors from R4? The vectors are coming from R4 where all coordinates are equal.
oh, so for this case, it will be 1. Yes.
It will be 1, right? Because the basis contains only one vector. We saw it before, right?
Yes, we have
There is
only
just
one
one.
linearly independent vector here.
Correct. That is also correct, right? And that is coming from basis, right? Because basis only contains linearly independent vectors. So how many ever linearly independent vectors are there in the basis? And basis will always contain linearly independent vectors. So it directly implies that how many number of vectors are there in basis will be equal to the dimension of that vector space or a subspace. Clear?
Yes, ma'am. Thank you.
Okay.
Small doubt.
Yeah.
The zero vector itself, if someone writes only the zero vector, is
Yeah.
it linearly? And someone asks whether it is linearly independent or linearly dependent. What will be the answer?
So yesterday I had answered this. So tell me this. If I have a set which contains zero vector, what is that set? A linearly independent set or a dependent set? Suppose I have 1, 2 and 0, 0. Okay. Okay. Let me write this again.
1, 2, and 0, 0, then it will become linearly dependent for sure. But I'm asking singleton only the 0 vector itself.
Okay. Okay. So this is, you get this. This is linearly dependent, right? Right. Now you are asking 0, 0. Correct?
Then, is this a valid question? Like, अगर एक vector रहेगा तो उसमें linearly dependent या independent
it
का कोई
is.
बात है?
Yeah, it will be. Okay. So this is linearly dependent because I have C not equal to 0 and linear combination of vectors in this whatever, say, P set. Okay. So I have, I can take 2 times 0, 0 and it will give me a 0 vector, right?
Yes, ma'am. So, ma'am,
So
if it is linearly dependent, then if we span with it and generate the 0 subspace, like the 0 space, the trivial space,
yes.
and then someone asks that what is the basis for this space, then what
so
will be the answer?
What is it? So, okay, tell me what will be the dimension of 0 space?
1.
It will be 0. No, it will be 0. Because in the basis, there are no linearly independent vectors.
So how will you span it? Like span of something?
What is the span of a 0 vector? 0 vector itself, right?
Yeah.
So this is a special case, we can say, but the dimension of a 0 space is always 0. There is no linearly independent vector in the basis of 0 vector, the 0 subspace. I think I have it in the slides. If not, I will add it. Is that clear?
Yes, ma'am.
Okay, cool. It's not clear. I'll elaborate that more. But I'll have to read a bit on this so I can make the correct claims. Fine. Fine. Okay. Now tell me what is the dimension of R2? Quickly, guys. 2. Fine. What is the dimension of R3? 3. What is dimension of R4? 4. And N. Right? So we got this. Right? Cool. Okay. This is your daily practice problem. You have to find a basis. And we'll do this tomorrow, that which is a subspace of R4 and where all vectors are such that their components are adding to 0. Okay. So we will do this tomorrow. Coming to what we have learned today. So this is clear to everyone, right? What the question is asking. It's similar to the question that we did. So I'm asking for a basis of a subspace, which is a subspace of R4, where vectors are such that their components are adding up to 0. So for example, there'll be vectors like 2, -2, 2, -2. Okay. And if I add them all, it's coming to 0. Fine. So give me a basis for this tomorrow. Okay. So what we have achieved today, or what we have learned today. So we understood what are vector spaces. We also understood what are subspaces. We also understood what are bases. And also we saw what is the dimension of a vector space. Fine. So this is all I wanted to cover today. So I'll just stop sharing and also I'll stop recording.